in particular, I do want to mention the difference between these two. Please pay attention. Potential is not the same as potential energy. Okay, one is symbolized with V, one is symbolized with U. Okay, so also we talk about absolute potential and potential difference. Okay, sometimes abbreviate as PD, potential difference. So potential difference is you compare 2 points, right? It's a property of 2 points, and absolute potential is a property of 1 point. You're finding the potential at a given location, whereas potential difference, you're finding the potential difference between 2 locations. For some reasons, I don't know why people do not like writing delta. I always write the delta when you're comparing changes or differences between 2 points when you have final minus initial. So it makes it very confusing when you read the textbooks, especially in the next chapter. I don't know if your lectures has covered voltages yet. Voltages is another word for potential difference. Okay, so every time I write voltage, I write delta V. It's much, much more clearer. You're comparing the voltage between 2 points, usually 2 points of the outlet or 2 points of the battery, the beginning and end point of a battery, right? That's a voltage of something. Okay, so make sure you understand the difference between this and potential energy. Again, you can have the absolute energy or a difference in the potential energy. So this is the potential energy difference. Okay. So let me talk about potential energy first, because a very similar concept is gravitational potential energy. Okay. So you are semi-familiar with that because at least you're familiar with gravitational potential energy on Earth. If I put a bracket on Earth, you know the formula is mgy, where y is the height. Where does that come from, right? So you understand if I find a gravitational potential energy on Earth at this location, you would tell me it's mgy, where y is the height of this. Well, the definition is this. Okay? So the electric potential energy, the definition is, so this is a symbol for definition. The definition is it's the work done to bring a positive charge, positive test charge, from infinity to a point. Okay. What does that mean? That sounds scary. So let's break this down. Okay, so electric potential energy, will symbolize it with U, and that is the work done. Okay, so that's the amount of work that is done to bring a point charge from infinity to a given location. Okay, why infinity? Let's break this down a little bit first. So what is work done? Remember, work done is force times distance. Okay? But if this is 3 dimensions, we need to make this a vector. And also maybe the distance is no longer x, it's just some general length. Where do we want to bring it? From infinity to r, at the location r like this. Okay, so this is worth remembering. I'll put this over here. Although the first line is the definition, I would say expanding it out with work done as well. This is the one that is actually worth remembering. So think about gravitational potential energy. What is gravitational potential energy? It's actually the same thing. It's work done to bring a positive mass, not charge, positive mass from some reference point to a given location. Okay, so the reference point, if you're on Earth, we set the ground as a reference point. Okay, so if I say U graph instead of U electric, is from the ground to some point instead of r, let's say some height, y, all right? If I'm only moving in this direction, so let's just consider y, okay? Let's not consider 3 dimensions, let's consider 1 dimension in the y-axis like this, all right? So if this is gravitational potential, we should put the gravitational force here. If this is electric potential, we should put the electric force over here. So the gravitational potential here is on the ground, we set y equals to 0. At a certain height, we'll put y, right? So the ground is 0, and then to height. What's the gravitational force on Earth? On Earth is mg, dy. But mg is a constant, right? M is a constant, g is a constant. You can pull that out like this. And then what's integrate y? Just y. And then plug in y minus 0. That's how you get mgy, all right? So how about here? This time we don't have an Earth because the Earth on overall is neutral pretty much. So we want to find, for example, the potential energy of bringing a point charge, a little charge Q at this point, all right? But you see we need a reference point. On Earth, we have a natural reference point as the ground. We set the U graph here to be 0 so that the U graph here is mgy. But here, where should we set it to 0? You need a starting point, some point to set it to 0. There's no more Earth surface. So the next point is 0. So here we will say the electric energy, electric potential energy of putting this charge over here at infinity to be 0. What does that mean? Is just saying that if you're putting the charge away so far away, this guy, this little q, can no longer see this guy. It's so far away. There's no energy influencing between these two particles. So there's 0 energy between them. The closer you bring this, right? So you see that integral is basically like an area, right? So the closer you bring towards here, the more energy it will, as you can see, that it will repel them more. So the closer you bring here, the more energy is stored, the more potential is stored between these two guys, right? If you bring it to infinity, it's going to be 0. There's no energy stored between these. This guy is barely significant. All right, so that's the absolute potential energy. You need a reference point, but how about difference? In gravity, if you move something from here to here, what's the difference in potential energy? You take mgy1 and minus mgy2, right? So here is the same concept. You take u2 minus u1. Now you can, oh, sorry, I should finish this off, is to solve here, what's the electric field between the two charges? The electric field between charges is q over here, right? So in one dimension, this is just dr. Okay, from infinity to r. There's a subtle minus sign. I'm not going to explain this in the short lecture here. So if you integrate this, kq is a constant. So you can pull that out, integrate 1 over r squared. That is just minus 1 over q. We'll cancel out the 1 in front, so it's just r like this. Okay. So this is the potential energy between 2 points like this. All right. So if you now take 2 points and you start moving them from this distance to a larger distance away, for example, like this. Okay. So if you move them further apart, then you can calculate the u over here, the final, as kqq over r2 like this, and calculate the initial, okay, between the 2 points. Use the same formula, but a different distance. And you can calculate the change in the electric potential energy. Okay, so you can apply a lot of things like change in potential energy is equal to the change in kinetic energy and find out how fast they will be moving or slowing down. So if these guys repel like this, right, so it'll start repelling and you try to find, let's say I start off with V equals to 0. After you calculate the change in electric potential energy, you know, by conservation of energy, the change in potential energy should be the equals to change in kinetic energy, and you can calculate what's the final speed if it starts at 0, for example, like this. So that's the use of that.